Yes. Thanks, Yana. Thanks for introducing yourself. The next speaker is Yana Kinderknecht, and she will talk about subordination principle and Feynman-Kac formulae for generalized time-fractional evolution equations. We are looking forward to your talk, Yana.
Yeah, thank you, Martin. Thanks for this opportunity to give this talk, and also thanks for the previous speakers, John and Sonia. Now I can save some time on the introduction because everything is already introduced. Not everything, but many things. This talk is based on our joint project with Christian Bender from Saarland University and my former master student, Marie Bormann. So the results can be found in these two papers of us. Okay, so preliminaries. First of all, if we start with the time homogeneous Markov process, then we have, if we have its transition kernel, which describes probability of transitions of the process, then we know a lot about the process. Namely, we can construct integral operators based on these kernels, and this family of operators is an operator semigroup. And for good processes and for suitable Banach spaces, sometimes it happens that the corresponding semigroup is strongly continuous. We may speak about its infinitesimal generator, and then this our semigroup provides the solution of the corresponding Cauchy problem for this evolution equation. So this L is the generator of our semigroup TT, and speaking on the language of stochastics, so this integral operator, due to this definition, is nothing else but the expectation of this U0 of psi at the time point t, when we start our process psi from the point x. So you see, so this is the formula which provides us solution to this Cauchy problem. And we say that this is stochastic representation of the solution of this Cauchy problem, and we say that this process psi is a stochastic solution of this evolution equation. Or we say that evolution equation of this type, of this evolution equation, is a governing evolution equation to this process. And coming back to what John Goff has said, so in this form you see that only one-dimensional marginal distribution of the process play the role in this representation. So we can actually think of many different processes, probably not even Markov processes, but with the same one-dimensional marginals, and we can use them to represent solutions of such evolution equations. And of course, we can rewrite this differential, so to say, evolution equation in integral form, and in the integral form it will look like this. It is u0 of x plus integral from 0 to t, and here stays lu sx ds, something like this. So please pay attention to this integral form. Okay, so in this context, basic example, basic couple is the process of Brownian motion, which is a stochastic solution via this formula, is a stochastic solution of the heat equation. And Brownian motion is the basic process in the family of diffusion processes, which are used to model classical diffusion. But nowadays, there are many observations which provide evidence that sometimes we have diffusion, but something goes wrong. Namely, the diffusion is anomalous in the following sense. So in the case of standard diffusion, a mean square displacement of a particle is proportional to time, and the underlying processes are Gaussian processes. And so sometimes when we are talking about anomalous diffusion, it may happen that diffusion is qualitatively slower or faster than the classical one, and it has the same speed, but the underlying processes are nothing to do with Gaussian processes. And as this heat equation is the basic equation of so to say standard diffusion model, then in the anomalous diffusion story, the basic equation is the so-called time and space fractional heat equation. So Laplacian is replaced by fractional Laplacian. So this minus is so these two minuses are attached to this is my notation of fractional Laplacian, and this first order partial derivative with respect to time is replaced by Caputo fractional derivative of order beta between 0 and 1. So in this form, I have written it as an integral equation. So we have a Riemann-Liouville integral. So integral operator with respect to time. So we have two components in this equation. We have L, which is a generator of a strongly continuous semigroup on some suitable Banach space, and we have a kernel K, so to say memory kernel in our story. And so once again, in the classical setting, one can obtain Brownian motion as a limit of rescaled, as a scaling limit of Bernoulli random walks. But if we replace Bernoulli random walks by continuous time random walks, that is, it is allowed for particle to make random jumps after random waiting times. So if our random jumps are big enough, this can speed up the diffusion. But if our waiting times are big enough, this can slow down the diffusion. And so these are two parameters, so to say, so this guy allows to speed up the diffusion, and this beta allows to slow down the diffusion. But their proper combination may cause to a speed which is the same as in the case of standard diffusion, but nevertheless, what about the underlying processes? And actually, this equation is well studied in the literature, and there are some stochastic processes which provide stochastic solutions of these equations. And these processes are completely from different classes of processes. So it was our starting point of view research. We wanted to understand why so different classes of processes can be used for solving this equation. So what is the best class, and what other classes can be used, classes of processes can be used, and how general could be evolution equations which can be solved by these classes of processes, and so on and so forth. So now I will present first our results, and then I will comment on examples and how it is related to already known things in the literature. So in our research, we consider the equations which we call generalized time-fractional evolution equations, and they look like this. So exactly as I presented before. So integral form, we have L, which is a generator of a strongly continuous semigroup on some Banach space. This U0 is initial condition, and it belongs to the domain of our operator L. And K is the memory kernel, or we call it memory kernel, which is a quite general kernel. Namely, we have actually only one assumption. It is a technical assumption on integrability. It looks like this. So if we consider this kernel K with respect as a function with respect to the second variable, so it should be a little bit better than L1 function for each fixed t. When t tends to 0, this guy may explode, but the explosion should be controllable, and so we should be able to control or compensate this explosion by means of this factor for some epsilon and for some alpha. And of course, there is a kind of interplay between two variables, t and s. The better the function k is with respect to the second variable, the worse it can be with respect to the first one, and vice versa. So it's quite general assumption. And so the question which we posed to us when we consider this general class of evolution equations, so which processes can be used to provide stochastic solutions of this evolution equation? And so first result, so we have made an interesting construction. So there are several steps. So first I present the construction, then it will be clear why it is so. So our first step was the following. So we're beginning with the kernel K, and on the base of only this kernel K, we construct a function phi in this way. It's a power series where coefficients are given in terms of kernel K. So it's just iteratively application of the integration with kernel K. So we start with 1, so constant function, and then iteratively integrate with respect to kernel. Well, so as a hint, yeah, this guy pops up as a solution of Volterra's second order equation by using just fixed point, Banach fixed point theorem, and this is a kind of a product of Picard iterations. That's why this type of formulas. Okay, so we have constructed this function, and so under assumption 1, that is under quite weak assumption 1, we have proved that this function is well defined and entire function with respect to lambda for each fixed t. Further, so this is just a summary of what I have already said. Further, we have second assumption, namely we assume that this function phi as a function of minus second argument is a completely monotone function. That is, it means that it is a Laplace transform of a measure which is concentrated on the interval from 0 to infinity. And this probability measure. Probability measure because at 0 we have phi of 0 is equal to 1 due to construction. So this means that, so if we assume that our function phi is completely monotone, then there exists a non-negative, for each fixed t, there exists a non-negative random variable a of t, such that its distribution has Laplace transform given by this function big phi. Okay, so this is our second assumption, and hopefully if I have time at the end of the talk, I will present some results where these assumptions are fulfilled, of course. Okay, so now the main theorem, the so-called subordination principle, under assumptions 1 and 2, for each positive t, we can define the operator, which we denote like this way, which is just integral from 0 to infinity. And here we apply semigroup generated by this guy L to phi, and then integrate with respect to the distribution of our random variable AT. So this is the subordination principle, because here we have a solution of the corresponding evolution equation with kernel equal to 1. Yeah, just ordinary evolution equation, no fractionality. And then we subordinate all this stuff with respect to this density of another process. Okay, so first step, we prove that this is a well-defined guy. For this, we use a Healy-Phillips functional calculus to prove this, but we have done it. So this guy is well-defined. And second, this guy provides the solution of this evolution equation. And yeah, initial condition is fulfilled in this sense. So once again, my evolution equation has two ingredients: kernel, memory kernel, and generator of a semigroup. And in the solution, you see this generator of a semigroup, and then a distribution of a random variable, which was constructed from the kernel only. Okay, so this is the structural solution of this big class of evolution equations. And as a remark, if we assume that our semigroup is generated by a Markov process, then that is, our semigroup has this stochastic representation, then also this operator also has stochastic representations, namely it has this form. So we see that as a stochastic solution of this evolution equation, we use this process. It is a Markov process psi, time changed by independent process A of t, which was constructed from the kernel. So in this result, stochastic solutions of these evolution equations have this subordinate form, Markov process subordinated by some other process, which is independent from psi. Of course, we can have here not only this case, not only semigroup generated by Markov process, but we can add potential, for example. And again, if this semigroup has a stochastic representation by Feynman-Kac's formula, then this guy also has a stochastic representation, Feynman-Kac's formula in terms of, so you see, I just, instead of t, I have A of t everywhere. So again, this is a subordination, this is this subordination principle. So instead of time, I have this new time, operational time. Okay, and of course, we can proceed further and consider here generate of some subordinate semigroup or Schrödinger group, and then we discussed time-fractional Schrödinger type equations. They are discussed in the literature, so to say, and so on and so forth. Okay, now second interesting result is the following. So if we consider kernels K, which have additional property, they are homogeneous of order theta -1 for some theta positive. Homogeneous, I mean that the following identity holds. Then as this random variable A of t, or this process A of t, we can use the following process. Namely, we have only one random variable A, which is given in terms of our function phi at time point 1, t equal to 1. And then the dependence on time is given by this multiplication with a power function. So we have splitted our subordinator into two pieces. One piece is random, this is this random variable A, and another piece is time dependence, it's just a power function. Okay, so example, let us consider the kernel K given in this way. This is exactly the kernel which pops up in time-fractional evolution equations. So you see, this is the kernel which is homogeneous, and the order of homogeneity is beta -1. So my parameter theta is just beta. And starting with this kernel, applying this procedure which we how we define our phi. So having kernel K, we construct phi explicitly, and this function phi is constructed, and it is, well, it is already a known result actually that I mean there are stochastic solutions which are known for time fractional heat equation, for example. So there is no surprise that our phi looks as it should look like. So here we have Mittag-Leffler function. I just look how much time I have. So this is a Mittag-Leffler function, and this function is completely monotone function for each beta from 0 to 1. So if we consider this kernel K, and for example, as L we take Laplacian, that is the corresponding Markov process is Brownian motion, then our result would be that we can obtain solution in this form, solution for time fractional heat equation in terms of this process. So this is the result of theorem number 2, that this process can be used as a solution of time fractional heat equation. But as we see, this kernel is also homogeneous. That's why, so here we have just A of t with this Laplace transform, any process. And but in particular, we may take this process. Moreover, we know that Brownian motion is a self-similar process, and hence one-dimensional distributions of this process are the same as one-dimensional distributions of this process. So here you see this randomness in the time changed is removed and replaced by random scaling. And now we have a time-delayed Brownian motion. And further, this Brownian motion with this time delay has the same one-dimensional distributions, marginals, as fractional Brownian motion with Hurst parameter beta half. This process is no more Gaussian, but in the literature it is known that time fractional heat equation on one hand has solution in terms of these processes. This is the so-called gray Brownian motion, and this is not Gaussian due to this random scaling, and this is not a Markov process due to since here we have fractional Brownian motion. But also here we have some other options, and these options I will present in a minute. If yes, I have still some time. But nevertheless, so you see. So here we have a subordinate structure of the process which provides stochastic solution, but we can also use some other processes. They do not have a subordinate structure, but they are good because this process is a self-similar process with stationary increments. What could be nicer in the sense of modeling. Well, so this is a basic example, but of course there are some further examples, and in particular our approach. So we start with the kernel. Kernel is given explicitly. Then we construct phi explicitly, and then we can find, theoretically at least, we can find the distribution of these random variables, A of t. So everything is constructive. Okay, so it was, so to say, second type of result. Of course, this is a corollary of the main theorem, the special case. Now we consider another corollary, namely we consider the case when our kernel K is of convolution type, namely the dependence on T and S is in this way, and this function K is a good function. In particular, we consider the case when our this function K has Laplace transform of this form. It is 1 over H for some Bernstein function H. If we have a Bernstein function H, this means that we have a random process called Levy subordinator, which has this H as a Laplace transform. So this formula holds. If we have this process, Levy subordinator, we can construct an inverse process called inverse subordinator, given in this form. And so the statement is that under assumption 1 and 2, and in this case, when we have such kernel as our process AT in the result of theorem 2, we may take inverse subordinator. And Markov processes time changed by inverse subordinators are known in the literature and are used in the literature to provide solutions of such evolution equations. Exactly in the case when we have a generator of a strong discontinuous semigroup, but only this type of kernels are considered, only those who are related to Levy subordinators and Bernstein functions. And again, example, the same example, time-fractional heat equation. We have the same kernel. You see it is of convolution type, this kernel. And actually the corresponding Bernstein function looks like this. We can apply corollary phi 4. So this chain I have already shown you, but now I have added one more guy here. So instead, so as this A of t, we can take not only this guy, but also this process. And this is inverse subordinator. So actually these two classes of processes were known in the literature as stochastic solutions of time-fractional heat equations. But so our approach allows to obtain everything as the special cases of our results. And I have a remark. So if we are in the situation of corollary 4, that is our kernel K is of convolution type, and Laplace transform of this function K is just 1 over H for some Bernstein function H. In this case, this equation is equivalent to the following Caputo type evolution equations, or Cauchy problem for Caputo type evolution equations with generalized Caputo type derivative, which is given by this H, by this Bernstein function. And this is the definition in terms of Laplace transform of Caputo type derivative. So these equations are equivalent, and hence our results provide solutions of this type of equations, which are discussed in thousands of papers on functional analysis. As special cases of such generalized time-fractional Caputo type derivatives, I can present, for example, usual Caputo derivative of order beta, then the corresponding Bernstein function is just a power function, a mixture of Caputo derivatives of different orders, and then the corresponding Bernstein function looks like this, and also the so-called distributed order Caputo type derivative. In this case, Bernstein function looks like this. So all of them are included in this, so to say, in this corollary from our theorem number 2. Well, and I have even 5 minutes, so I can present even more examples of kernels. So as I said, our approach is the following. So we have equation, that is, we have L and K, and starting from the K, using these Picard iteration techniques, we construct phi. So sometimes we are lucky to construct phi explicitly as a power series, so we are able to recognize this function. It's a special function, and in some cases, then it is known how the so it is Laplace transform of what. sometimes it is known. So let me present an example. And now it's about fractional calculus. So it is about Marichev-Saiga-Maeda kernels. First of all, many terrible special functions. So there is the so-called Appel's third generalization of the Gauss hypergeometric function called F3. And with the help of this function, you don't have to look at the formulas. So it's just something terrible, but nevertheless. So on the base of this generalization of hypergeometric function, we construct a kernel which looks like this. This is our kernel, the so-called Marichev-Saiga-Maeda kernel. It is a power kernel, and then a function, this special function of these variables. And these guys pop up in Marichev-Saiga-Maeda operators of generalized fractional calculus. And it turns out that this kernel is actually a homogeneous kernel of this degree of homogeneity. The integrability condition is fulfilled. So our assumption 1 is fulfilled. So we can apply theorem 2, and we're able to construct the corresponding function phi. And it is given in terms of 3-parameter Mittag-Leffler function. And it is known under which assumptions on its parameters this Mittag-Leffler 3-parameter Mittag-Leffler function is completely monotone. Hence, there is a corresponding random variable. And in this case, then we obtain everything. So this is just a long story about these parameters. But after all, we obtain. So this is an example of a kernel which suits to our assumptions and provides a nice result. That is, function phi is constructed explicitly. And moreover, this guy, 3-parameter Mittag-Leffler function, it is just a special case of Fox H function. And there is a function, this fractional calculus, which allows to calculate Laplace transforms of H Fox functions. And their Laplace transforms are given again in terms of Fox H functions. So the distribution of the corresponding random variable A of t can be given explicitly as a particular Fox H function. Moreover, first of all, about special cases, when we choose particular parameters of our 3-parameter Mittag-Leffler function, then it reduces to 2-parameter Mittag-Leffler function, and the corresponding kernel K looks like this. And if we consider even more special choice of parameters of Mittag-Leffler function, then it reduces to 1-parameter Mittag-Leffler function, and this is how our kernel looks like. In particular, as a special case of this special case, we obtain kernel of generalized Gray-Brownian motion. So choosing this B and A, we obtain the kernel of generalized Gray-Brownian motion. That is, so this this Marichev-Saiga-Maeda kernel is a general class of, rather general class of kernels, which includes, in particular, the kernel of generalized Gray-Brownian motion, and also this kernel of standard time-fractional kernel. Moreover, one more remark. I see that I have no time, but just the last remark is that there is a book of Virginia Kiryakova and some papers of Virginia Kiryakova where it is shown that actually all operators of fractional calculus can be, including these Marichev-Saiga-Maeda operators, they can be represented as iterated applications of Erdődy-Kober operators. So these Marichev-Saiga-Maeda operators are somehow 3 times iterative application of Erdődy-Kober operators. And one can, in a similar way, one can consider more iterations of Erdődy-Kober operators, the corresponding kernels, and everything should work in a similar way, because all these things then are related just to these Fox H functions on this level and on the level of their inverse Laplace transform. And there are some results in the literature when these Fox H functions are completely monotone, and hence one can speak about stochastic solutions. Okay, so thank you very much for your attention. I'm finished.
Thank you very much for a very nice talk, Yana. Are there questions, remarks?